So part B on problem 2 asks us to estimate whatever answer we have from part A using Stirling's approximation. So let's just write down the answer we have from part A. It's 4n factorial divided by n factorial divided by n factorial divided by 2n factorial. And Stirling's approximation I'll just write here. Is n factorial for large N can be approximated to 2 pi n root of 2 pi n times n to the e, n over e to the n, right? So this is Stirling's approximation. Now we need to use this to approximate whatever answer we have from part A. Now this is just quite literally plugging in the values of Stirling's approximation for the numerator and the three terms in the denominator. So why don't we just start doing that? What is 4n factorial? Let's just move this away. What is 4n factorial? Using Stirling's approximation, it's 2 pi root of 2 pi 4n times 4n. I'm just going to move that a little further down. 4n over e to the 4n divided by root of, for the n factorial, root of 2 pi n times n over e to the n times root of 2 pi n over e to the n times square root of 2 pi times 2n over e to the 2n. Now what do we notice first? We can cancel out one of these root 2 pi's with that. Now let's pull all the constant terms out, right? So we have root of 2 pi times root of 2 pi times root of 2 and 4 on the numerator. So we have root of 4 on the numerator. So this 2 and this 2 will get cancelled with that 4, let's say. So overall we're left with 1 over root 2 pi, right? So we have a root pi from there, and that gives us a pi, and the 4 gets cancelled with these two 2's, and we have a root 2 out, right? So we have 1 over root 2 pi times, now let's look at the lone n factor which is not under an exponential. So we have n gets cancelled from there, root n gets cancelled. Now we have two root n's remaining, so we have a root n which comes out, times. Now let's actually work on the exponentials. So let's just split this up into constants, n's and e's, right? Constants as in the numbers, n's and e's. So let's take out the number first. So the numerator becomes 4 to the 4n, then n becomes n to the 4n divided by e to the 4n, whole divided by. Now let's pull out the 2's. 2 to the 2n times, let's pull out the n's, n to the 4n, because there's n, and 2n, so it's n to the 4n, divided by, we have again e to the 4n. So here we see that e to the 4n gets cancelled with e to the 4n, n to the 4n gets cancelled with n to the 4n. Let's denote this as some constant cn, which is equal to cn times 4 to the 4n divided by 2 to the 2n, which is equal to cn times 4 to the 4 divided by 2 to the 2 whole to the n, which is equal to cn. I'm just going to write this all the way to the left. So let's go all the way here, which is equal to cn times 4 to the 4 divided by 4 to the n, which is equal to cn times 4 to the 3n, right? So this 4 gets cancelled to give 3 there. So it's 4 to the 3n, which is equal to cn times 64 to the n. So let's just write cn out just as a final answer, which is equal to, oops, oh no, that was a mistake, sorry. Yeah, so that's fine. So it's root 2, whoops, why is that happening? Yeah, okay, alright. So it's root 2 times pi n times 64 to the n. Now the question asks, is this an exponential? Rather, it asks, is it essentially an exponential? We see that this n term it doesn't stand a chance against 64 to the n when n becomes a very large number, right? So this is in fact essentially an exponential. So yes, it is an exponential, because the term which dominates in the end is 64 to the n. So we have, yes, it is an exponential, and the question asks, if so, it is like what to the nth power? So this is like 64 to the nth power. The answer is 64. Right. So that's the answer for question 2, part B.